Good afternoon, ladies and gentlemen. My name is Chiravachradej. Today we will focus our lecture on a topic that they call combined stress. I put on a bracket of the axial stress because this is only the combination of the axial stresses. The reason we have to think of in terms of combining, because we have learned how axial force cause axial stresses onto a cross section. We also learned that separately, bending moment also create axial stresses on a cross section. We actually analyze the two stresses, the two causes of axial stresses separately. What happens if the material is subject to axial forces and bending moment at the same time? Okay, this is the topic that we will deal with it. Okay, to go through all this, then we will start talking about what we should know, what we should learn before we begin to analyze this, beginning to learn how to cope with this combined stress. Then we'll talk about the concept of how we see the combination, and then that will be applied, the concept will be applied into mathematical model later. Then we'll talk about a case study. This is what we call the off-centroid loading. Well, we will look at it, I will explain what it is when the times come. Then we look at another example, just a normal one that is not the off-centroid loading. Now, what do we need to know? Of course, we need to know the fact that these combined stresses happened, and then this is when we need to calculate it. Okay? It is when there are bending moments about different axes. Okay? For example, the bending moment can come about z-axis, and it's also come about y-axis, as we discussed. And then because of the concept of the neutral axis, of this each moment we have different neutral axes, meaning the distribution of the axial stress will be different according to the neutral axis. Then we have to separate the two cases and then combine them later. Okay? Or maybe we could have one axis of bending moment in the second case. Then we have the axial force. Of course, the axial force, the distribution of stress is equally all over the cross section. That's why it is equal to the axial force divided by the total area. Whereas the axial stress for the bending moment, the distribution will be straight line, as we see. So we will have to combine the two effects into one another. Or in the worst case scenario, there are two axes of bending moment, plus we also have axial forces, meaning we have to separate the three cases. Right? We have to understand the area moment of inertia very well here, because it's about how it rotates and how the distribution of stress will be relating to the axis of rotation. We also have to understand how we cope with axial stresses, and then of course how we calculate the stress from the bending moment. Now, once we grasp the idea of this, then we probably could continue. Well, the underlying theory is what we call superposition concept. Okay? For example, here. Well, we talked about the superposition concept already when we do the force method for the axial force. Okay? The same idea apply here. If on this cut section we have axial force, we have bending moment applied on that cut cross section area. Okay? Now, because we know that distributions are different, we don't know how to calculate them together. So what we do is we use the separate case like this. We said that we could consider this cross section as if it is the effect from the axial force N, and calculate what actually happened with the bending moment. Once we get the result using the superposition concept, then we could combine the effect. As you see, the axial force actually create an equal distributed stress, whereas the bending moment on one part, in this case smiling bending moment, on the top is compression, at the bottom is tension. Okay, then we combine, because we can calculate these two stresses, then we can combine, maybe it becomes that kind of picture. Okay, and then we can calculate them all. That is just the concept, and of course the calculation will follow this concept. We calculate whatever stress caused by the axial force and whatever caused by bending moment, then separate the two cases, then combine the result together. This is exactly what we're going to do. Now, let's talk about the case study we talk about. We're talking about what we call off-centroid loading. This is rubber, the same rubber I have been using to demonstrate the effect of axial force and the effect of bending moment. Now, if we actually thinking about this in terms of my demonstration of how axial force or axial stress work, this is the way it is. Okay, notice that it should go down straight into each other, and then when I release, it separate straight line. No bending, it just shorten and then become the same. Or if I pull it, of course it will be longer, and then release it, become the same length. Now, watch this carefully. One thing that I haven't actually mentioned before is that my two fingers, the thumb and the middle finger, actually press at the centroid or about at the centroid of the area. Okay? Notice it's about the middle of the this cross-section area, right? So, what happens if I actually move my finger a little bit, one finger, outside the centroid? My thumb will be on the centroid, my middle finger will go into this edge. If I press down straight, notice that there will be some bending. Okay? Release that way. If I change the side, you see in the hand, my thumb at the centroid, okay, and my middle finger on this edge. Notice that it bends. Okay? What this does demonstrate is that if the point load, the axial force, doesn't fall onto the centroid of the area, it creates bending moment. Don't forget, axial force associated with just shorten, no bending, no curvature, just shorten, longer, shorter, longer. The one that causes curvature is bending moment. So, moving out of the centroid, if the point load or the axial force moving out of the centroid for whatever reason, then it creates bending moment. And that is the case we're looking at. Okay, let's see. This is example. Okay? If we have, well, a beam. Okay? This beam is assumed to be weightless, or basically the weight is negligible. So small, it doesn't have to count. Okay? Then there's fixed support on the left hand side of the beam. On the right hand side is a free end, no support. However, there is a point load pressing in. But this point load doesn't press onto the centroid. Right? This is the centroid. Right? That point load actually pressed below the centroid. Okay? But on the same line as the height. Okay? But it's below the centroid by 5 centimeters, as it indicates here. Now, the question wants to know what is the stress level at the edge 1 down here and at the top there. Okay, 2. It also would like to see the stress distribution through the height, not through the depth, through the height, which means this way. Okay? Of the cross section of the beam. Let's see. Okay? Now, of course, we need to know the two stresses, the axial stress and of course the axial stress caused by axial force, and we also want to know the axial stress caused by the bending moment, which had the two different formulation here. Well, but we learned about the formulation and we seen how to apply it already. So the next task is to find axial force. The area can be calculated. Find the bending moment. I and Y, I think we know how to measure it. Okay, I can be calculated, and Y we know how to measure it. Okay, so here is the cut section, right? I cut it and then at any point, at any length, and then draw the right hand side free body diagram. So we can see the point load 120 and the axial force N, actually because of the normal distribution, the equally distributed of the axial stress caused by the axial force is always on the centroid. Okay, and then of course in this case will be the bending moment coming in. Sigma Fy, because if we assume that the beam has no weight or it can be neglected, then of course there will be no shear for this picture. Now, if we look at this, we should realize that if we do sigma Fx equal to 0, then we have the axial force, the normal one. Now, if we do sigma moment about point O is where the load N is acting. Okay, this is point O here. Notice that the bending moment is not 0 because this force P have an arm. You should notice that the bending moment is not 0 because the load P has an arm, has a 90-degree arm. That 90-degree arm is 5 centimeters. Okay, so the bending moment has to resist the rotation of point O, and it equal to 5 times 120, 600 meganewton centimeters. Okay, now about the area then, about the cross-section area then. The property we have the area that we have to calculate here, right? Then we also have to find I. Let's talk about axis first then, okay? If that front view is XY, your cross-section area will be Y and Z, okay? Now this bending moment here that we draw, okay, on the 2D plane, it will have to be around Z axis, okay? Therefore, our neutral axis must be on the Z axis as well, and it must go through the centroid. So that is our neutral axis. Okay? Meaning everything we measure will be from that line, 90 degree, and from that line for the bending moment stress. The area, then we calculate the normal, rectangle. Okay? The I, of course, since that is the neutral axis, the 90 degree to the neutral axis is the one that we square up. No, so not square, sorry. We cubic up. Okay? So it becomes that formulation for the I, and of course, as I said, why we measure here. Okay? Since we know, we calculated already, N is equal to 120 compression, bending moment is 600 meganewton centimeter Z phase. Okay? Then of course, we calculate the stress for the axial forces, axial force, simply N over A, and then of course for the bending moment. Now because we want to know the top and the bottom, if we measure Y from here, neutral axis up here 20, down here also 20, so it's the same. However, it is tension, Z phase, tension on the top and compression at the bottom. Whereas the axial force is compression, therefore the axial stress from that axial force is all compression. Now, when we combine, then on the top, we don't really combine. On the top, because one is tension, one is compression, the combination of the effect is minus one another. And that's the equation. Then of course, that's the answer as well. At the bottom, because they both are compression, when you combine the effect, it becomes even more compressed. Therefore, the mathematical model is positive, is plus, and both become compression. And that is the other answer. Now, How do we this? We know that on the top 25 compression, at the bottom 175 compression. How does it is built? Fact is this: axial stress caused by axial force is a constant, the same throughout the cross section. Axial stress caused by bending moment is a straight line function. It means that when you combine, then it still becomes the straight line function, and that is the way it is. Notice that the length of the beam has no effect on the bending moment, because this time the load coming this way, 90-degree distance is that way. Therefore, it is the same bending moment throughout the beam. For this case, of course. And that is the answer. Okay, let's see the next example, shall we? Yeah. Just a beam, okay, with one distributed load. One of the support is apparently 45 degrees to the horizontal line. The beam is horizontal beam. Now the cross section, however, is not really a normal rectangle. Apparently it's a hollow section, right? A rectangle and then a rectangle hole. Okay. Now we want to know what is the axial stress at point 1 and at point 2. Where is that point 1 and point 2? That point 1 and point 2 is at point B here. At point B, which means 0.5 meter from the pin support. Again, before we start, let's have in mind what we are calculating. We are calculating the combined effect of the stress. Of course, this is axial stress caused by axial force and caused by bending moment. Okay? Therefore, the first task we should do is find out the axial force, find out the bending moment, then of course the area and the second moment of area. Okay? There we are. Now to find axial force, to find internal forces in this picture, we need to find out reaction first through the total free body diagram there. The three equations, three unknowns, the same step we have done all the time: sigma fx equal to 0, sigma fy equal to 0, sigma moment equal to 0. Not necessary in that order. I have to repeat here, not necessary in that order. Okay. There we are. But after we apply all three equations, we should get out all reactions, three reactions. Once we get the reactions, then we can move on to the next step, calculating the internal forces at point B, then we draw from A to B. Okay? Once we got that, then we calculate again with the three equations. Now, we don't need shear force here, so since we can get axial force and bending moment straight away, might as well do it. Then, once we get axial force, we get bending moment, then the same pattern happens. Okay, let's go analyzing the cross-section area. Now, we need area. In this case, simply, I will use the big rectangle, then minus the hole. Okay, and then we should have whatever left, that is the solid body here. Okay, use the same concept. I will use the same concept with the eye. Notice that this one here, the bending moment come about z-axis again. Therefore, the neutral axis here is also on the z-axis, and it has to pass through the centroid. This picture here is symmetry. Okay, this cross section here is symmetry. If it's symmetry, both top and bottom, both left and right. If it's symmetry on both axes, then the centroid must be at the center, mid height, mid width. So it must be here, the neutral axis. Therefore, when we calculate I, we realize that it has to be the one that is 90 degrees to the neutral axis, that we cube it. Therefore, here we are. That is the I for the total picture. That is the I of the hole, that hole here. And then we calculate I, simply that. Okay? So next is we know everything. The only thing left that we need for the calculation is y. Y at point 1 and y at point 2. Okay, but we just measure 90 degrees. So there we are. Y at point 1 is 5 centimeters, right? 90 degree. What? Measure up. Then Y2, Y of point 2, from neutral axis, measure down, right? Total of 20. Then the substitute. Okay, axial stress caused by axial force for point 1, we substitute 5. Now, because this one here is smiling, remember? This bending moment here is smiling, therefore on the top, compression. Above the neutral axis, compression. Below neutral axis, tension. Okay? Then, of course, compression and compression, then you combine them. And then you get the answer of the stress at point 1. Then, what about point 2 then? Point 2 y is equal to 20 is measured below neutral axis. Again, smiling face. Below neutral axis, tension. That one is compression, but this one is tension. Therefore, the combination of effect is not really combining the effect. It is actually counteract the effect. Therefore, the sign minus there. Okay, and then we get the answer. And that is a summary of our answer. Now, should we move on so that I can summarize this lecture then? Okay. Well, the main focus is starting. We need to understand the concept first, which is again the superposition concept. It just calculate two cases separately, then combine the effect. Okay, the axial force by the axial stress by the axial force, axial stress by the bending moment, and then we combine them. Okay, and then we see example. One example is what we call the off-centroid loading, where the point load doesn't apply on the centroid of the cross-section area, which create the bending moment as we see. And that concludes the lecture for today. Thank you.